speaker is our colleague and friend Jaime Mata-Falcon from ETH Zurich, and he will talk about interlayer reinforcement for digitally fabricated concrete structure. So please, Jaime, the floor is yours.
Good morning. Thank you, Liberato, for the introduction and for the invitation to participate in this interesting event. So I'm Jaime Mata-Falcon, senior researcher at the chair of structural engineering at ETH Zurich. Chair is led by Professor Kaufmann. And today we'll present this project within the NCCR Digital Fabrication, which is a large collaborative project. We are working on this interlayer reinforcement for digitally fabricated concrete structures. And I think this is, we are not the only ones working on this concept. I think you will see with Frickbos and Victor Mechterine will show also slightly different approaches with this idea. But before entering into the details of the interlayer reinforcement, I would first like to give a quick overview of the different reinforcement concepts we have at ETH Zurich for producing digitally fabricated concrete structures. And in our group, we're mainly working in these 4 technologies you see in the slide. And on the left, you have technologies in which we are digitally fabricating first the reinforcement. And this reinforcement is used as a non-conventional formwork to either cast or spray the concrete. This is the case of Mesmol and Netcrete. And on the right, you see more additive manufacturing of concrete. So the primary focus is on the producing this concrete element, but in order to produce a structural element, we need to find like a suitable reinforcement strategies. Before going to the right part on the left, so I would like to quickly introduce first thing in Mesmol. The idea is how we can produce complex walls without formwork or without a conventional formwork. And here the idea is that we robotically fabricate a reinforcement cage, which can be complex of double curvature, and we use small diameters, so then the spacing of the rebars is small, and this allows, as you can see here, to cast the core of the structure without a conventional formwork. So the reinforcement is both reinforcement and a permeable formwork. Then the cover is sprayed, and here this example is the DFAB house. We produced it 3 years ago, but now we are in new phase in the industry implementation of the technology. So we are collaborating with Peri and Sika, and the improvements have been moving the fabrication of the river cages to a prefab environment. This allows to have continuity of reinforcement in both directions, which was not possible in the previous phases. And also this speed up the fabrication quite a lot. The idea, so we prefabricate these cages, we bring them on site, we assemble them, and then Sika has been improving the casting process. I think it's the idea now is to use almost conventional concrete mix, slightly modify in order it does not flow out of this reinforcement cage, but at the same time it has good compaction and homogeneous properties. Then you see that we are spraying, we are performing structural tests to see, I think the behavior is quite similar or to a conventional structure. We still have to see about the bond because we have the reinforcement in between the core concrete and the spray concrete to see if we have exactly the same bond or slightly less bond than in a conventional structure. So this is Mesmol. We have conventional rebars. And then in Netcrete, we have textile reinforcement. Here you can see a bit detail of this knit candela structure built in Ciudad de Mexico. And you can see that we have a textile which serves as base for this spray layer, and to have this cell structure within the interior part, we have the colors of the textile. And here, well, in the first phase of knitcrete, the idea is just to have the textile as a stay-in-place flexible formwork. So here it's like a small bridge prototype. So place the textile with some tensioning elements, and then we spray it with some cement paste to have enough stiffness in order to be able to cast or spray the concrete on top. But what we are interested is in using this textile not only as a formwork, but also as the reinforcement for these cell structures. And there are two possibilities. So we want to use structural yarns here, so aramid, carbon, or glass fibers. We are having a look. And one possibility is to directly knit with these structural fibers, or other is to have a conventional or a non-structural fiber that is knitted, and then it's guiding and straight inlays, which is much more convenient. And we are doing a study to see if the cement paste coating or the more conventional epoxy coating, how they perform. So this is an extensive experimental campaign done by the, I think, doctoral student is Minuli working on this topic. We have done uniaxial bending test, and also now we are analyzing the shear capacity. I think this then is like textile reinforcement, but with some particularities, because we are not applying the coating in an industrial environment, and also in these structures maybe we have as you saw in the previous slides, we have the textile and we have only coating and concrete in one side, so we have some particularities, but the behavior is quite similar to textile reinforced concrete. I think Victor Mechterine will show also some their process at Dresden, in which the mechanical behavior is not very different than what we have here. Good. Now going to this additive manufacturing of concrete. So at ETH Zurich, we have digital casting systems and 3D concrete printing. And both use the same material science concept. So it's in both cases, we use a set-on-demand process. So we accelerate the concrete before placing it. And in 3D concrete printing, we don't have any formwork. So we are extruding. And in digital casting systems, the idea is that we have a minimum formwork. There are various possibilities. And you could think, why using this minimum formwork? So it's much better having this process like 3D concrete printing without formwork. And I agree, but regarding the reinforcement, we could see some advantages in having this minimum formwork, in which we can cast around the reinforcement, because we are not placing the concrete on top of the previous layer, but we are casting, so we have a bit more of flexibility, and we are able to do, in some cases, this casting around the reinforcement, which is a quite conventional structure. But in some cases, for digital casting systems, and also in all cases for 3D concrete printing, so we cannot place a reinforcement sticking out, and for this, we think that the concept of having an interlayer reinforcement after printing one layer plus adding then post-install reinforcement is quite interesting. But before going to this topic, I would like to give very brief introduction to these digital casting systems. This is a family which started with this smart dynamic casting, where the formwork, this minimum formwork, was slipping, so slip forming technology. And there are other possibilities with plastic paper formwork. The idea here is we have a set-on-demand concrete process, so then this minimizes the formwork pressure. So we can use this plastic foil that with some tension. This slide, you see, I think, the Excel technology. Here, the minimum formwork is like a 3D printed ultra thin plastic formwork, which at the same time is filled. And then the formwork can be removed after casting, after the concrete has hardened, and can be recycled for printing a new formwork. Here is just a geometric exploration with branch structure, which we can leave some openings to in its element to have this post-tensioning cables. But here in this slide is more related to this casting around the reinforcement, which I was mentioning. In this structure, the future tree is this column we produce with the Excel technology. The idea is, so we pre-print this ultra-thin formwork. Then we have our rebarcates. We insert it inside and we cast with the set-on-demand concept. So this, whenever this is possible, is very cheap and is leads to a same structural performance as conventionally cast structure. Okay, but now we go to 3D concrete printing. We cannot place these rebars sticking out. There are some approaches to insert them, but it's not super easy to do this. And the concept here is, we can apply it for both for 3D concrete printing and for dynamic casting systems. But imagine that we have a beam. So when we design a beam, we have the main reinforcement is, the bending reinforcement is taking the main loads. And then we have some shear reinforcement, which does not need to have strain hardening. So when we are designing with stirrups, we are putting just 0.1% of stirrups. This does not allow for a beam to have a hardening response in the transversal direction. But we can redistribute the compression field, and even with a softening response of the shear reinforcement, we can reach a hardening the response, a deflection hardening of the beam. This is what we want when designing structural elements, to have a tactile behavior. So here the idea is, we are printing, so this beam we will print it in vertical. We are printing layers, and in every layer or every other layer, we place an interlayer reinforcement, which is used for shear. This can be fibers, I think cables, which was implemented quite a time ago in TU Eindhoven. And also there are possibilities. This has been also done, I think, to manually place small diameter rebars in the interlayer. So then you print the element with the shear reinforcement, and you leave a void where you post-install this. It could be a tendon, or it could be a pre-bent bar. So I think this can be pre-stress reinforcement, or we can grout it or not. So there are several possibilities, but it is important that I think this, in case, for example, the fibers, we are using it as shear reinforcement. If we want them to take the main loads, it's quite challenging to have really strain hardening and sufficient ductility with fiber reinforced concrete. So one of the possibilities for interlayer shear reinforcement, we started 4 years ago to say, what about placing conventional steel hook fibers on top of a 3D printed layer, or here on the left you see for Excel. So after we have done a casting interval, and this, instead of placing the fibers into the concrete mix, we add them separately. So this has the benefit that we do not modify the rheology of the concrete. Also, we can use inexpensive long steel fibers. We can place the fibers whenever we need them structurally. Another benefit is also that, we can leave some part of the concrete close to the surface without fibers. So then these fibers will not rust, which is a static problem when we have steel fibers in the mix. So this is, the concept with fibers, and we have done this testing campaign, which I would like to show you a bit more in detail, in which we have, for the bending reinforcement, we have two concepts. I think in series 1, we had this post-tensioning, in this case, were post-tensioning bars without any bond. Then in series 2, we have passive reinforcement that was placed here, so in this bottom void of the cross-section, and then it was injected to have proper bond. And for the shear reinforcement, so we wanted to compare, okay, what about having this thin cable with high strength? This is around 2000 megapascals, to compare with the performance when we have these aligned fibers. And this is for series 1 and series 2, the geometry, these beams in 4-point bending around 1.5 meters in span. And the 4 first beams were this with this post-tensioning reinforcement. And here, since we don't have bond in the longitudinal reinforcement, as soon as we get, we have decompression of the cross-section and the first bending crack appears, so all the deformations concentrate in this bending crack. So this is not, we cannot have a ductile behavior in such structure, independently that, putting with fibers gives some, toughness, but it's more interesting, and I will focus in the next slides in this series 2, which we have for 5 specimens, we have same longitudinal reinforcement, 2 bars of diameter 26 of conventional reinforcement. Then we have 2 beams without any shear reinforcement, 2 beams with these aligned fibers of 0.3% and 0.6%, and then 1 beam with this continuous cable of 0.1% amount. And then in the next slide, you see a bit detail of the production. So this is the print pass of different series, and this is the interesting detail. So I think we don't have, or when we were producing these beams, we did not have an automation of the cable or of the fiber placement. This was proof of concept, and they were placed manually, both the fibers and the cable. And then we speckled the samples and instrumented with digital image correlation to measure continuously the crack kinematics in this test. And here you see the results of loaded deflection and here on the right you see the crack pattern at failure. And first, maybe focusing these beams without, here it says no reinforcement, but it's no shear reinforcement. So we still have the longitudinal reinforcement. So maybe at around 40 kilonewtons, we have like the bending cracks up here. And then around 100 kilonewtons, first shear cracks appear. And as soon as we have the shear cracks, they open and we have a quite brittle failure. And then when we add this interlayer reinforcement, I think the fibers or the cable, so the shear crack appears at 100 kilonewtons, but we are able to really to have a hardening response of the beam. And then finally, so for the cable, so we were breaking the cable, and for the fibers, we were having a pull out of the fibers.
Couple of more minutes, Jaime, please.
Good. Yeah, I'm almost finishing. So with the fibers, you see that the cable is much more efficient because, of course, we have 2000 megapascal and it's a continuous element. So then we need like 4 times more amount of fibers in order to reach the same capacity of the cable. Good. So then the cable for ultimate limit state is quite convenient, but in this slide I'm showing, so these are the same beams, but this is the load crack opening response. So here we were selecting the point of the cracks with the largest opening, and we were plotting it over the force. But here, well, we are not plotting the crack opening, but let's say the vertical projection of the crack opening. But what is important here is that with the cable reinforcement, so as soon as we have the crack, the shear crack, we need a large crack opening to activate the cable because it's a smooth cable. And here at the serviceability range, which is this point, we have converted to crack width, we will have around 1 millimeter. This means that the serviceability design of these beams are more restrictive than the ultimate design. Then with the fibers, we have these hook fibers. So the bond seems to be quite better. So when the crack, the shear crack is opening, we have a quite reduced crack width, which is favorable for the serviceability design. So I think this is why I think we have identified that the bond of the reinforcement in this interlayer reinforcement is critical. And we have established a collaboration with Costantino Mena and Laura Esposito from the University of Naples to have a closer look to this bond. And with this, I would like to thank to all the people in the NCCR Digital Fabrication working on this topic. Thank you for your attention. And if you have any question, please do not hesitate to send me an email. Yeah.
Okay, thank you, Jaime, for this nice overview and for these results that you have shared with us. I have seen that in the Q&A box there are already a few questions for you, very precise.